Have you ever just looked at an AI, maybe a character in a video game or one of those self-driving cars and wondered, how in the world does it know what to do? You know? It can feel like some kind of magic, but it's not. It's actually a puzzle. And today, we're going to put together the first, most important pieces of that puzzle. All right, let's jump right in.
I mean, seriously, think about it for a sec. A self-driving car has to make thousands of decisions every single minute in a world that's always changing. It's got to see pedestrians, understand what a traffic light means, react to some other driver who just cut it off. So how do you even start to program a machine to handle all of that chaos?
Well, the very first step, way before you write even one line of code, is you have to give the AI a really clear job description. And in the world of artificial intelligence, we have a special name for our AI. We don't just call it a program or a robot, we call it an agent.
Okay, I know this definition looks a little academic, a little technical, but trust me, the idea is actually incredibly simple. An agent is just anything that can sense its world and then do something about it. Think about a simple thermostat. That's an agent. It perceives the room's temperature with a sensor, and it acts by turning the heat on or off. A self-driving car? It's just a way more complex version of that exact same idea. Perceive and then act.
So, to build any kind of successful agent, engineers need a blueprint, a formal plan, and this is it. It's called the P's framework. You can think of it like the spec sheet for any intelligent system, and you have to define these 4 things perfectly. P is for performance measure. What does a good job actually look like? E is for environment. Where is this thing operating? A is for actuators. What can it physically do? And S is for sensors. What can it see or perceive?
All right, let's make this real and just apply it to our self-driving car. For its performance, the goals are pretty clear, right? Safety is number 1, obviously, but also speed, keeping the passengers comfortable, and of course, legality. It's got to obey the speed limit. The environment is basically everything outside the car. The roads, traffic, people, the weather, you name it. What can it do? Well, its actuators are the parts that take action, the steering wheel, the accelerator, the brakes. And finally, how does it perceive all this stuff? Through its sensors, a whole bunch of cameras, GPS, radar, sonar, the whole shebang. Just by filling this out, we've taken this massive, complicated problem and given it a clear, manageable structure. Okay, so we've defined what the car needs to do, we've got its job description, but that doesn't tell us how it makes a choice, like hitting the brakes instead of the accelerator. For that, our agent needs a language, and not just any language. It needs one that is totally, completely, mathematically precise.
You know how we talk to each other? If I say, hey, it's kind of chilly in here, what does that actually mean? Is it 68 degrees? 50? Our language is full of this stuff, ambiguity. And it's totally fine for us humans. But for a computer, it's a complete nightmare. An agent needs a language where every single statement has one and only one possible meaning. No room for interpretation.
And this slide just nails that point perfectly. Look at the English sentence. You can have A or B. So does that mean I can have A or B, or maybe both? It's vague. Now look at the logic on the right. It's so exact. It says, you can have A, or if and only if you do not have A, then you can have B. This is what's known as an exclusive OR. It means one or the other, but never both. See that? Zero ambiguity. That is the level of precision an AI needs to work reliably.
And this powerful language is built from just a few really simple parts. You got propositions, which are just statements that have to be either true or false, like the traffic light is red. Can't be kinda red, it either is or it isn't. Then you have operators like and, or, and not that let you connect these propositions. And finally, you've got rules for building more complex thoughts from these simple little blocks.
All right, so we've got our blueprint, the PAS framework, and we've got our super precise language, which is logic. Now, how do we connect the two? This is where the agent's brain really starts to come to life, turning what it sees into what it does.
It all comes down to really simple rules. The agent's sensors are constantly feeding it information about the world. For instance, a camera, one of its sensors, sees a red light. The system takes that raw data and turns it into a logical fact. The proposition, red light ahead, is now set to true.
And that simple fact, that true statement, acts like flipping a switch. It triggers a rule. If red light ahead is true, then execute the action, apply brakes. And that command goes straight to the car's actuators, the physical braking system. And there you have it. A perception from a sensor led to a logical conclusion, which triggered a physical action. That's the entire loop right there.
So here's the big secret. A self-driving car's amazingly complex, intelligent-seeming behavior isn't happening because of one giant genius thought. Not at all. It's the result of thousands, maybe millions, of these tiny, simple, logical if-then rules all working together in perfect harmony. The complexity just emerges from all that simplicity. It's an incredible idea, and it's the foundation of almost all AI.
And that, right there, is the big takeaway from all this. AI isn't some strange, unknowable magic. It's a structured, careful engineering discipline. You start by clearly defining the problem and the world it lives in. That's the PAS framework. And then, you give the agent the tools to solve problems in that world using the clean, precise language of logic.
So, we've successfully mapped out a blueprint for a self-driving car. But what happens when the jobs get more complicated, more human? How would you even begin to write the PAS framework for a doctor, or a research scientist, or an artist? What's the performance measure for a great painting? What's the environment for a scientist making a breakthrough? Suddenly, it gets a lot harder. And thinking about that really shows you just how far AI has come and how incredibly far it still has to go.